At time t equals 0, the position vectors r meters and velocity vectors v meters per second of two particles A and B are as given below. So RA is 5, -3, VA is 2, 1, 4, RB is -10, 27, -8, and VB is 3, -1, 5. Show that if these particles continue with these velocities, they will collide and find the time of collision and the position vector of its location. Okay, we don't necessarily need to use the dot product of the relative velocity and relative displacement. We could do it something like this. We can say RA at time t is, so we remember we're using these two vectors here, and it's going to be 5 plus 2t, -3 plus t, and 7 plus 4t. And then RB of t, which is going to use these two vectors, is going to be -10 plus 3t, 27 take away t, and -8 plus 5t. Now, all we need for collision is to find t using, say, the I component, and then check that it works for the j and the k components. So for this one here, we're going to have 5 plus 2t is equal to -10 plus 3t. Rearranging, that gives us t is 15. Now if we go back and check, when t is 15, this one would be 12. And so with this one, so the j components work, and this one would be 67, and so would this one. When t is 15, the I component here would be 35. 2 times 15 add 5. So we've got the time and we've got the position vector at 35, 12, 67. But just to show you how the dot product does work, we'll use it to find the t, and then you would just repeat the sort of process. So the ARB would be RA take away RB, and if we do that, we get 15 take away t, -30 plus 2t, and 15 take away t. And that means that AVB, which we can just get from these here, is just going to be -1 to -1. It's the coefficients of t in ARB. And then if we dot those, so we've got 15 take away t, -30 plus 2t, 15 take away t, dot -1 to -1 is equal to 0. So that gives us -15 plus t, take away 60 plus 4t, take away 15 plus t, and that is equal to 0. So that gives us 6t take away 90 is equal to 0. 6t equals 90 gives us that t is equal to 15. And then we would just go back and find the position vector.